here. Okay, now let's see what we have. Okay, so question number 1. Design an algorithm in pseudocode to find the third largest element in the list. Yeah. So this question, I received many different ideas, and some of you have the big O n square algorithm. Most of you have big O n log n algorithm, but just only few have the big O n algorithm. So it's a test, so I know that it is very hectic. So that's why even if you have an big O n square algorithm and you analyze it correctly, the algorithm is correct, you still have 40 points. Okay. But for the students who spend time and design an optimal algorithm, meaning big O n algorithm, then I will give some bonus points to the student, right, who had an optimal solution. So let's see what is an optimal solution here. Let's say we have a list of numbers like this. This one is a bad one because it's already sorted. Okay, so let's see. Let me have an arbitrary set of number 5, 7, 6, 1, and then 2, 8. Okay. So if we have this list of numbers, then obviously you can use the sorting algorithms you learned in the class. Sort it first, right? And then just count the third element from the right most position, and then you have it. Okay, so that's it. You can sort this one, and some of you use insertion sort. That is a big O n square, right? And some of you use heap sort or say merge sort. Then you have big O n log n. But it's not an optimal solution for this. The optimal solution is what I presented here on the shared document. So basically, what I will use is that I will use 3 variables. Okay, I have here is v1, v2, and v3 to keep track of what is the biggest value and what is the second biggest value and what is the third biggest value when I try to scan from left to right. Yeah. So at the beginning, I will just have the first one here. Yeah. And then I will have this one is minus infinity and minus infinity, or in other words, the mean value when we use Java or C. Okay, then we have the mean, right? Okay. And then I will start from the second element, okay, and compare. If it's bigger than the current biggest, then I push this one down, right? So now I have 5 here, and I have 7 here. Okay, so continuously I will try to see what will happen to the next, right? So that said, I just have to scan from left to right, right? And at every position, I just compare first with the biggest. If it's not bigger then I compare with the second, right? And now it's bigger than the second. I push this one down and insert it here, right? So every element here, I just have to have 1, 2, 3 comparison at most. The worst case is 3 comparison. The best case is just only 1, right? So that's why I will have here, if I count all of the comparison, then you can see that the first initialization takes 3 steps, and then the for loop will take n steps in total, right? And then the if here will have n minus 1, but depending on how many steps do I need, right? It can be 0 for the mean, it can be n minus 1 for the max, okay? So that's why we have the best case, the worst case, and the average case. They're all big O n, right? So in fact, we just have big O n steps for doing so, okay? That said, if you have the big O n square, that's fine. You will have 40 points. But if you have big O n, then you have some bonus points, okay? So the second question is very similar to what you had in the assignment. And then the best approach here is the double recurrence tree, okay? And the double recurrence tree we already practiced many times in the class. So in these two questions, Tn is big O n square for both of them. Okay. The third question is about Hippify, or using the Hippify for inserting a new element, okay? So in fact, I already asked you, okay? We went through the design for extract marks, right? And then finding a max value on a heap. And I asked you to do this as an exercise at home. So if you did it at home, as I asked you, then you should not have any problem for doing that, right? So that's it. For example, we have a heap here, and if we insert a new element 14, right, then we simply insert it at the last position, right, and then do the reheap that up instead of reheap down, right? So from here we reheap up, right, and we will bring 14 here, 10 down, 8 down, 2 down, right? Okay, so what would be the worst case? The worst case is the height of the tree. So it's big O log n, right? So what is the total number of steps? The worst case equal log n. However, when the heap is already full, then we have to extend the heap by copying. For example, the heap currently occupies the whole array. Then we need to have another array with one more element, and then we copy. Then in that situation, we may need a big O n step. Okay, but as far as you identify the big O log n, you will have the full number of points. Okay, and then use your algorithm to insert 12. It's an easy thing to do. Just reheap up. Then you have 30 points for this question. All right. And it's simple, isn't it? Okay. So that's it. During the class, pay attention to the lecture and then try to finish the exercises I asked you to do, like insert a new element in a heap. Okay, so by doing so, it reminds you about the content that you learn in the class, and also it will make you ready for the test, because I like to pick some of the questions I asked you in the class for the test. Of course, I will ask 4 or 5 questions and then just pick 1 or 2 for the next test or so. Okay, that is about the test. Any question or so? Is it clear? All right, very good. Okay. So before we move to the next topic, meaning quick sort and also answering the question, is there any kind of sorting algorithm that can do better than n log n? That is what we have currently with merge sort, heap sort, and also quick sort you will learn today. Okay, so we will try to answer the enhanced questions about sorting algorithm. Uh, Before we go to that, let's try to plan for our training for the programming contest. Okay, we have to be prepared for the next North American programming contest for universities around not only not only Louisiana, but also the southern part and the whole United States. Okay, so I will try to train one or two teams depending on how many students are interested. So last time when I asked you to answer the questions about what would be the best time for you, right? Then most of you said that say 5 p.m. After our class on Thursday would be the best thing for you. So we will do it. But first, can you log or register into the training website that I have last time I posted? Let me show it again here. Okay, so you can see that we have the training website at tran.selu.edu, and then slash dom backslash dom just, right? And if you go there, then you will be asked to log in. If you don't have an account, then you have to register. Register is very simple. You just have your uh, username. Usually you can use your, short name, or you can use the W number. That is fine. But accessing to this website, you have to be on the university network. Doing so, you can go to desktop.southeastern.edu and log into your student account, and from there you can access to this website. Okay, if you are outside of the university, if you are on campus, simply log into this tran.selu.edu and backslash Dom Church. Okay, I already posted 3 problems. The problems here are pretty simple, and actually is about what you are learning. Okay? Sorting and how to use the sorting algorithm to solve some real-world problems. Yeah. So we have 3 problems, P1, P2, and P3. Just click at the problems, then you have the description of the problem, input, a sample input, sample output, right? And you can submit your program in any programming language. So right now you can submit in Java, C, C++, Python, and if you prefer other languages, I can add the new languages in, but I think with the current status of the website, it's on my server. So I can handle that. I can add the new language in, but I think it's more than enough for us. So try to go through the posted problems, and then next Thursday, not the coming one, right? But the one after this coming Thursday, I will have, and let's say, a review about the problems I posted here and discuss the solution with you. If you have an idea, we can discuss that, right? And after we discuss the pseudocode or the idea, then you can write down the program and submit the program. Yeah. Once you submit the program, my server will run your program through a bunch of sample inputs, actually testing inputs, and compare the output with the output from your program. It's not limited to the sample input and output I posted here. There will be more additional tests to be sure that your program is correct. Okay, so if you have time, please log into that training programming contest training website. Try to work out one or two problems there before I discuss the solution, and then you submit the programs. Okay. All right. So the next topic is about quicksort. So I guess you learn about quicksort, right? At least in data structures in CMPS 390. Okay. So the quicksort is very simple. It's very similar to the merge sort. So you have a list of numbers and you want to sort it, right? Okay, let's say here I want to sort this list. So the merge sort is that we will try to partition this list into two parts. Okay. This is the merge sort, right? So for the merge sort, the way we partition is that we will partition the list right here in the middle, right? And then apply the merge sort for the left half, apply the merge sort for the right half, merge the result, right? For quicksort, it's a little bit different. We also partition the list, but we don't partition it in by cutting it in half, right? So we partition that around a pivot. Let's say here, if I choose 5 as a pivot, then I will try to partition this list into two parts, one with the elements lesser than 5 and one with the element bigger than 5. Okay? So it's a little bit different. But then we will analyze what is the complexity of the quicksort. And it turns out that quicksort is much faster than merge sort and answer heap sort. So we will discuss about that, why it's quicker, why it's faster. But now, first we will try to have one example. Let me have a different example so we can practice with that. Okay, so let me have example I already prepared. Okay. All right, so let me turn this one off so we can pay attention to the whiteboard. Okay, so we will have a list of elements like this. Okay, so here are the list of numbers that we want to partition. Okay, we have 10, 17, and then 12, 6, 19, 23, and then we have 8 and 5. Okay, so we want to sort this list of numbers, and first we will try to partition this list into two parts by first choosing a pivot value. Here's the pivot value. Okay. It's very simple. In this example, I just choose the first element is the pivot element. Can I choose any other values at the pivot? That's fine. I can choose the last one, or I can choose the one after the first, or the one before the last, or the middle one. Any, okay? But here, I will try to use the first element as the pivot, and then I will partition this list into two parts. The left one, the left half, or the left subarray has elements less than 10. And then the right subarray will have elements bigger than 10. Okay? So I will use 2 pointers. One to point to what I call the left wall. That is the place where I will swap the element that is, say, smaller than 10, okay? And then I will use another pointer. Yeah. This one I call I pointer, or the keeping track of the left wall. This one I call J pointer, okay? So now, first, I will choose the first element as the pivot, right? And then set the I pointer here. Okay. I will start the J pointer from the 17, which is the next element. If it's bigger than the pivot, I don't do anything, okay? Because I want to keep the bigger one on the right of the I or the left wall here. So if it's bigger, it's already bigger than 10. So I skip that. So I will go here. Okay. Now it's still bigger, so I don't do anything, but I move to the next. So I will right here. So we will go row by row, right? Okay, so when it's at 6, let me have the position. Okay. Here I have 1, 2, 3. We can have it from 0, no problem. 5, 6, 7, 8, right? Now it's smaller. So we know that it has to be on the left of 10, right? So what I will do is that I will advance this one and then swap these two positions. So now I will have 6 here and 17 here. Everything else will be the same, right? So it means that I have 10, and then 12, and then 19, 23, 8, and 5, right? So that's it. Here, after I swap, the other elements is still on the list. So to make it simple, I will simply remove the elements that is unchecked, right? Okay, so I will remove that one so we can pay attention to the values. Those have been changed or have been swapped. Okay. So after we swap, we increase the J, right? So I is here, and we just have the J starting from 2 to N. Okay, so just one follow, right? So here we have it's 19. 19 is bigger than 10, right? We skip it. 23, now we have it at 8. Okay? So that's it. Once we are here, right, you can see that it's smaller than 10. So what I will do is that I will advance the I, which is the left worm, that maintaining the values lesser than the pivot on the left of that, right? Okay, so that's it. We will increase this worm to here and then swap the values. So here I will have 8 and 12 swap, right? And now I will advance the J pointer to the last. Now it's still smaller than 10. So again, I will advance this I to here, right? And then swap. Now, when I advance it to here, the value I have is 17, right? So I will have it 5 and 17. All right. And now let me fill out the values that we have so far. So here I have 10, I have 6, I have 8, right? 10, 6, 8, 5, right? And now I have 19, 23, right? And then 12 and 17. So you can see that here on the right hand side of the I pointer, I have here all of the values are bigger, right? And now the last step I will do is that I will swap the value at J pointer with this. Then I will have the last result, that is 5, and here I have 10. So I will return the R value here, right? As the point where I partition the original list. And now you can see that here I have 5, 6, 8, right? And then here I have 19, 23, 12, 17. And then apply the quick sort for the left subarray. Apply the quick sort for the right subarray. Okay. So that is the partition for the quick sort. Now, let me show you the algorithm again, and then we will talk about the differences between quick sort and merge sort. Okay, so here is the quick sort, right? Partition the array from P to R, and we have the pointer here. Apply the quick sort for the left. Yeah, actually, we can go from P to Q minus 1. That's fine, right? And then we apply the quick sort again for the right subarray. So it's very simple with merge sort, right? But if you implement the quick sort, it's about 50% faster than merge sort. Why? Can you see any difference between the quick sort and the merge sort? Remember that merge sort is also partition, but we partition it by simply jumping to the middle, right? Cut it right there. So that said, we have quick merge sort A from P to the middle, and then merge sort A from the middle to the end of the array, and then merge the two subarray, right? Okay. Can anyone tell me why quicksort is faster? Why quicksort is faster? In your opinion, what makes the quicksort faster than the merge sort? Okay, now I will ask you this question, and if you answer that, then maybe you can find the answer. Right? Remember that for merge sort, we will try to partition the list into two parts, right? By cutting it at the middle. And then apply the merge sort, and then merge them. How can we merge them? Can we merge the result using the same array that we start with? Given an array of elements, right? Cut it in half, merge sort the left, merge sort the right, merge them. Can we just use the original array for that purpose? Actually, no. For merge sorts, you have the left sorted, you have the right sorted, and then we merge them. You cannot simply merge them using the original array. You need to have an extra array to keep track of the result. Otherwise, you will mess the value up. Okay? So that said, you need to have an array. Let me remove this one so we can see it. So we need to have a different array with the same number of elements, and then we try to merge them, okay, into this array. So we do need, after let's say we sort this array, right? So we have 6, 10, 12, 17, right? So we have 6, 10, 12, 17 for the left. Of course, we have to apply the merge sort. So let's say here I have 6, 12, 17, and then here I have 5, 8, 19, 23, right? So I have the left sorted by cutting in half again and then merge sort again. But the question is about merging. Okay? So we have to have a new array and going from left to right, right? Writing it here. Okay? If we don't use a new array, you write here on top of 6. Okay? So you cannot keep track of the left and the right anymore. So you have to copy 5 to the first element, and it's not the case if we choose the original array. Okay, so that is the question. Yeah, and quicksort can do it on the same array. No need to merge, right? We simply go like I did before, and now we have 2 subarray on this original data set. So that is the main question. I mean, the main difference between merge sort and quicksort. Yeah. Quicksort also divided by 2, but no need to merge, meaning that we don't have the new array in order to copy, right? So copying is something expensive if we have a big array, right? So that's why quicksort is a little bit, actually 40% faster if we implement that one correctly. So that's why quicksort, the main reason why it's faster is that there's no need to use extra memory to copy. Okay? That is the main difference between quicksort and merge sort. Before we go into analyzing the complexity, let me ask you this. Now we see that quicksort is faster, right? Believe it is about 40% faster, right? But do we still need merge sort? Okay, we have merge sort and we have quicksort. Okay, looking at what I just explained to you about the extra memory space, right? Quicksort is faster, but does it mean that we never use merge sort? Yeah, we do. We still need merge sort. The reason for that is the quicksort, as you see from here, right? Originally we have this, and then we go down to here. We assume that the set of elements can be fit into the main memory, meaning that we can allocate an array that store or that keeps the elements we want to solve. But nowadays, with the internet, we know that the search engine has to search much more data than what they can store inside the RAM or the main memory of the computer. Okay. In that situation, we have to use merge sort because merge sort does not require us to have all of the numbers in the main memory. If the list of numbers are too big, right, we simply bring half of them into the main memory, right? Or when half of that is still too big, we just bring in 1/4 of that data into the main memory. And then when we copy, we can use the, say, SSD in order to keep track of the merging data. Right? You cannot do it with quicksort because quicksort requires that we need to have the data on the main memory. So in other words, both quicksort and merge sort are still useful. Yeah. If the data is small enough, meaning that we can fit them into the memory, quicksort is the best. But if it's too big, we will try to use merge sort in that situation. Okay. Now we will try to analyze the complexity of the quicksort. Now, can someone just tell me what is the best case, worst case, and average case for merge sort? Complexity. They're on and log n, right? Okay, very good. Okay, now let's see what we have for the quicksort. Remember that for the quicksort, we would have to partition the array into two parts and then apply the quicksort for the left and apply the quicksort for the right. Okay. So what is the worst case situation for quicksort? What is the worst case situation for quicksort? Now, let's see what will happen if I have the list is already sorted. Okay, let's see the best case first. Okay. Actually, the worst case is the best case. Okay. Let's see, I have here 1, 8, 9, 10, 12, 14. It's already sorted. Okay. So what is the complexity of the quicksort? Remember that when we have this list, we just need to have 2 pointers, right? The I and the J. The I starting here and the J will go from 2 to the end and then compare, right? If it's bigger, do nothing. It's smaller, advance, and then swap, right? Okay, that's it. Comparison just take only one step, swap another step, right? So for the partition, what is the complexity? The partition take big O(n), right? Where n is the number of elements. Okay? Now, quicksort for this case. Remember that it will be, if you have n elements, then what is the cost for sorting this? It will be the cost for sorting the left. Okay, partition first, right? Partition first, and then quicksort the left, quicksort the right, right? Okay. Now for this situation, what do we have for Tn? This one is the smallest one. So when we partition it, the left has 0 element, right? The right has n minus 1, right? So that said, we have Tn is T0 plus Tn minus 1 plus n. T0 is 1, right? 1 plus n is n plus 1, which is also big O n, right? So that set is about Tn minus 1 plus n, right? Okay, so what is Tn? It is already sorted. That's why I said that the best case for the input is actually the worst case for quicksort. Okay, so it will partition the first time here, and now for Tn minus 1, partition here, right? You have n minus 2, and then n minus 3, right? So can someone solve this one for me? Tn is Tn minus 1 plus n. What is it? What is Tn after we solve this recurrence? So we can use the recurrence tree, right? So it will be what? Big O n square. Very good. Okay. So it will be actually n plus n minus 1 plus 1. Right? This one will be n times n plus 1 divided by 2 is big O n square. Right? Okay. So that's it. If the list is already sorted, quicksort will span big O n square steps. Right? Okay. But in fact, for quicksort, we can assume that the list is not sorted because verifying whether or not a list is sorted take how many steps? N step. Very good. Yeah. We just scan from left to right, and then if this one lesser than this one, lesser than, lesser than, lesser than, lesser than, then the answer is yes, right? So that's it. The worst case for quicksort can be avoided easily by big O n steps, right? So that's why we don't pay attention to the worst case here. We want to pay attention to the average case. So that said, the worst case situation is here. The worst case situation is that when we have a list of elements, we will break it into this set and the rest. And then again, this one will be broken into this and the rest. Okay, so here is Tn, and here is T0, or you have only one, right? Here you have n minus 1, right? And then here you have n minus 2, right? So one element of T0. Okay, so that's it. The worst case situation is when the partition have 0 element less than the pivot and all of the elements bigger, right? Same thing, partition this one again. So what is the best case situation? The best case situation is that when we have a list, and then the partition will be, you have 2 halves that have almost the same size, right? So that's it. you have here the left and the right. And then again, the partition here, you will have half of this, right? Okay, and again, partition. So in that situation, you have Tn is 2 times Tn half plus n, right? So that is the best case situation for quicksort, meaning that we partition the list and then we have a balanced tree. Okay. And then using the recurrence solving approach or method you learned before, what is Tn? Tn is 2 times Tn half plus n. It's similar to merge sort, right? So what is Tn? Okay, so that said, the best case for quicksort is n log n, similar to merge sort, okay? N log n for all situations. Okay. Now, the worst case, we know that quicksort is n squared, but as I mentioned before, we can avoid the worst case by checking whether or not the list is already sorted, right? The best case situation is similar. Okay. So it's not helping us to saying that quicksort is better than merge sort. We have to be able to analyze the average case. The average case of quicksort, we need to show that it's also n log n. The same like merge sort, but it's faster because quicksort does not need to have an extra array for copying. So that's why it's about, say, 40% faster. It's a constant number. Let's say quicksort is, say, 60% of the running time for merge sort. In terms of complexity, it's not a big deal, okay, because they are both n log n for average case, but quicksort is constantly faster by about 40% because it does not need the extra memory for copying. Yeah, that's why in practice, quicksort is faster, even though it has the same complexity for the average case. Now, we have to be able to analyze the average case for the quicksort. Let's do it here to see what we have for the average case. Okay, first thing first, how can I calculate the average case for quicksort? Very simple question, okay? Remember that the average case means that we have to identify all possibilities of the input and then take the average number of the total number of steps or operations we have to perform. Okay, so for an input of size n, how many possibilities we have for quicksort? Here we have n elements, right? How many possibilities we have for partitioning this least. The first possibility we already saw in this situation, right? So meaning we have 0 element on the left and then n minus 1 on the right. And this one is the pivot, right? So it's one case. The second case is that you have on the left one element. Here's the pivot. And then here you have n minus 2 element, right? So here you have 0 on the left of the pivot. Here you have 1 on the left. And then the next case is that you have 2 on the left. And then the pivot. And then n minus 3 on the right, right? So here you have 0. Here you have 1. Here you have 2, right? Okay, etc. Until the last case is that you have n minus 1 on the left and 0 on the right. Okay, so those are all possibility. Okay, 0, 1, 2 until n minus 1. Okay, so here you have n possibility. So if we add all of the cost divided by n, then it's the average case, right? So let's write it down for this one. Here you have Tn is T0 plus Tn minus 1 plus n, right? This one, you have Tn is T1 plus Tn minus 2 plus n, right? So same thing here, Tn is T2 plus Tn minus 3 plus n. And the last one you have, Tn is Tn minus 1 plus T0 plus n. N cases, right? For, say, here you have 0, 1 to n minus 1. Okay, n possibility. So now, the cost for the average case of quicksort is, if you add the cost for all of them together, divided by n is what we have, right? So the average case is what? Tn is the average, right? How do I sum all of them up? Here I have the sum of Ti for I from 0 to n minus 1, right? Add all of them. Now, add all of this is also Ti for I from 0 to n minus 1, right? Here I go from T0 to Tn minus 1. This one, I can add them in the reverse direction, right? So that set is 2 times of Ti for I from 0 to n minus 1, right? And then here I have n squared, okay? N plus n plus n, n time is n squared. If I divide this one by n, that is the average case, right? So here, all possibility, you have Tn, 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 okay. Add all of them, divide by the number of cases, n cases. Then you have the average case is the total number of cases divided by n. right? And now we have to find what is Tn. We have to find what is Tn. Have we solved a recurrence like this before? Have we solved this one before? No, we have not solved anything like this before, right? Because in the past we solved, let's say Tn is 2 times Tn half plus something, right? But this one is the whole sum. So we have not seen something like this before. But can we solve this? Yes, we can. Okay, so you will learn a technique that will be used many, many times when you analyze an algorithm similar to what we have as quicksort here. Okay, so average case. All right, so now our goal is to solve this one, right? And what I will do is that instead of divide by n here, I will multiply this one to both sides, multiply n with both sides. Then on the left-hand side, I have n, tn, and then on the right-hand side, I have 2 times the sum of ti for I from 0 to n minus 1 plus n squared. Okay? So now, what I want to do is to get rid of the sum of ti here. Okay? So in order to get rid of this one, I will use a technique for getting rid of the sum. It's very simple. Here is Tn, and then I will substitute n by n minus 1. Then what will I have? The same formula, but substitute n by n minus 1. Then I have here n minus 1 times Tn minus 1. And then on the right-hand side, I have the sum of Ti for I from 0 to n minus 2, right? Plus n minus 1 squared. Okay? Now, what will happen if I subtract this two sum? Can you pull out a piece of paper and tell me what you have after you subtract these two sum, left by left, right by right? What will you have? Okay, pull out a piece of paper and let me know what you have. I'll give you about, say, 2 minutes. Okay, I think it's enough. Okay, after you finish, just type in a message saying what you have. The left-hand side, the right-hand side. Okay, now here you have NTN minus this, right? On the right-hand side, this sum will be cancelled because this sum is nothing but this sum plus Tn minus 1, right? So 2 times Tn minus 1 plus n squared minus this. N minus 1 square is n squared minus 2n plus 1, right? So this one will be, so n squared minus n squared minus 2n, it will be 2n minus 1. Okay? Bring this one to the right-hand side. On the left-hand side, you have n. Tn is, bring this one, n plus 1 times Tn minus 1 plus 2n minus 1, right? It's lesser than 2n. Okay? So it's what we have after we subtract. And now you see that we get rid of the sum here, right? We have Tn on the left, Tn minus 1 on the right. Okay? One more thing we have to do. So we will divide both sides with n times n plus 1. Divide both sides with n times n plus 1. Here you have Tn divided by n plus 1 is Tn minus 1 divided by n, right? Plus here, 2n divided by n times n minus 1 is 2 divided by n plus 1. Okay? From here to here. It's easy because we divide both sides with n times n plus 1. N will be cancelled, we have n plus 1. N plus 1 will be cancelled, we have n, right? N will be cancelled, we have n plus 1. Okay? So here's what we have. Now, we have one more thing to do because we have not seen this kind of recurrence before. So what I will do is that I will have a substitution. An is Tn divided by n plus 1. Okay. If I substitute Tn divided by n plus 1 by An, the left-hand side here I have is An. The right-hand side here I have is what? An minus 1, right? Plus, with here, I have 2 divided by n plus 1. Okay. If I can solve An, then I just plug it in here. You can see that An will be something, right? Plug it in here, then I can know what is Tn, right? So now, here is what I have to solve as the recurrence. Okay? Now, if I use the double recurrence tree, this one An will be 2 divided by n plus 1 plus 2 divided by n plus 2 divided by n minus 1, etc. Right? Okay, what is that sum? Okay, so in order to solve this one, I ask you to check your knowledge with discrete math. Right? What is the sum of 1 over I for I from 1 to n? Okay, a hint is as follows. What is the integral of 1 over x dx? You learned in, say, calculus 1, right? Okay, so we need to solve this one. I asked you to check this at home before coming to the class on Thursday, right? And this one, just remind yourself, and I will explain that to you. What does it mean with discrete math? And this one is in calculus, but we look at this one from a computer science point of view, then you will know how to solve this sum. And once we can do that, go back here and we can solve the recurrence here. Okay. Oh, if you did not take calculus, then okay, you don't have to check this, right? But just check this out. Okay. All right. All right. So, any question? Okay, Adam Graves. Yeah, it's correct. Yeah. All right. If no question, then I will stop here. So before we leave,